So we have seen expectation. Expectation was not good enough to describe a random variable because there were examples, right? It did not account for the how far your random variable could be from the mean, right? There could be cases when your random variable never takes the expected value. And in some sense, to capture whether you stay away from the expected value most of the time, or you are very, very close to the expectation all the time, you define this measure called variance, right? And it was expected value of x minus ex whole square. We could have taken x. We actually wanted to talk about x minus ex, right? That was the intention. But x minus ex, if you just take the expectation, positive and negative terms could cancel out. So now you can take mod, you can take square. Mod is not good because, right, it's not like a nice function, right, in the traditional sense. So we take square, and that gives us this very nice formula again from linearity of expectation, right? So this variance, this is the definition by which you will understand what is variance, and this is the way in which you will calculate variance. And if you can come up with this, coming to this is very easy. Okay, so it's your call whether you want to remember it, you want to derive it every time, but you have to understand why we define variance. And then whenever you see a random variable, most of the time to get ideas about random variable, you want to figure out these things. What are the variance? What are the expectations? And this is the thing for today. We will see a lot of examples of random variables. Some of them you have already seen. Some of them you will see today. And what we are going to do today is to precisely figure out their expectation and variance. Okay. One small thing, a very, very related quantity. Sometimes people like to talk about standard deviation when they are deep into random variables and they don't have the time to take square and square root. Standard deviation is just square root of variance. So not like just remember this, right? Sometimes you talk about variance, sometimes whatever standard deviation, but essentially the same thing. With the square, this is in some sense normalized because in variance you took x minus ex whole square. Any questions about these aggregate measures, right? It is clear why we call them aggregate measures, right? Clearly because they don't tell you the value of x at every, no, they don't tell you the value of random variable at each point. Point is point element of sample space, right? So they are not telling you, okay, what is x omega 1, x omega 2, x omega 3. They indeed tell you only the aggregate property of the random. And these are more important when you talk about traditional random variables, which you encounter mostly in your life, right? And this we tend to remember. Array, this is binomial random variable. We have seen it before. We know the properties. Oh, this is exponential random variable. And this we will see today. So these names will become more and more familiar as you go through not just this course, your life, right? In computer science, you will keep encountering these random variables and you will see why they are so important. Okay, let us start. What do you think will be the simplest random variable?
Sample space, we define the function which only give the value at
X omega is equal to, but omega need not be a number, no? So we are talking about only real valued random variables. But okay, you are thinking of simple in the sense of a simple function, but I'm saying something which you encounter most of the time. This is winning or losing, right? You do a random experiment, you win with certain probability, you lose with certain probability, right? That happens many times. You toss a coin, you get head with probability P, you get tail with probability 1 minus P. We'll forget about head and tail, true and false, winning and losing. We'll just remember any kind of random variable where you get 1 with probability P and 0 with 1 minus P is called Bernoulli random, because Bernoulli was the kind of the first one to recognize its importance. And you can kind of see that this is very, very important, right? I have written 1, 0, but if I had written 1 minus 1, things are not going to change much. If I had written 2, 0, things are not going to change. It's essentially the same random variable, right? If I can calculate the property of x, then I can calculate the property of 2 times x. If I can calculate the property of x, then I can calculate the property of x plus 1. Right? These functions are very, very simple, and you can translate the expectation and variance easily. And that's why the standard Bernoulli random variable is when you take the value 1 and 0. So please calculate the expectation and let me know what is the expectation. Right? You don't even have to multiply. This is one of the easiest one. You have 1 times probability of x equal to 1, 0 times probability of x equal to 0. This will give you p. And since you have calculated already expectation, why don't you tell me what is the variance? How will you calculate it? Just by formula, expectation of x square minus expectation of x whole square. What is the expectation of x square? Again, very, very simple. Just one term. So this is p square minus p square. Yeah, so the probability is p, right? The probability doesn't get squared. 1 gets squared, right? So this is 1 square. So let me just do it since this is the first time. Expectation of this is p square. This is 1 square times p plus 0 square times I don't care. So this is p minus p square, p1 minus p. Fine, this was simple. And this is something which you will encounter many a times. So let's go. Let's make our life more complicated. Binomial random. And this is something which you also have seen many a times. This is when you kind of repeat your Bernoulli random variable, right? You go to casino multiple times, even though I advised not to, right? So every time you go to the casino, you win or lose. Let's say you go to casino 10 times, x1 is first time whether you win or not. Let's not worry about how much money you are winning. Let's say this is a casino where you win, you get 100 rupees. If you lose, you get 0 rupees. In that kind of a casino, x1, did you win the first day? x2, did you win on the second day? So on and so forth. Right? So how much money did you earn at the end of n days? That's called the binomial random variable. And if I want to be precise, I can write it as x subscript n, where n denotes the number of repetitions, number of times you repeat the Bernoulli random. Right? Good. So what is the expectation? How will you calculate the expectation? Good, very good, right? So now you will again see the power of linearity of expectation. If I want to apply linearity of expectation, xn is x1 plus x, sorry, I need some other notation, no? I have two xn's. This would seem like a power. Okay, let's just assume that there are n, we will figure out a notation later, right? So now by linearity of expectation, this is expectation of x1 plus expectation of xn. This is n times expectation of your favorite xi, which is n times p. That was easy, right? What if you want to calculate it directly? Can you try calculating it directly? What is the probability that x is equal to k? You get k successes. In n repetitions, what is the probability that you get k successes? N choose k. N minus k, right? So now you know this, and k varies from 0 to n. Very good. So then you can calculate the expectation. Why don't you try? this is the kind of summation which you want to calculate. It's definitely not as easy as applying linearity of expectation, but this will probably require some JE kind of skills, and it will help to know that the answer is n times p. Anyone who got the answer? How many people got the answer? Just raise your hand. One. Okay, I will give more time. You can try calculating the variance now if you have calculated the expectation. Other people, if you're stuck on expectation, why are you stuck? Where do you need help? What is bothering you? I am the oracle which can help, but you have to ask the right questions. No, everyone is fine. How many people got it? Okay, good. So essentially, the important trick was, you know, you have k and you have k factorial. Let's make it k minus 1, right? And then we want to make it n choose or n minus 1 choose k minus 1. And that we can do by borrowing n. Let's actually take out n times p. Is that okay? I have just taken np out and kept the term so that they look nice, right? And then what is this quantity? Come on, this is not even JE, it's n minus 1. See, you answer quickly, you will be released from this lecture sooner, right? So it's in your interest to answer me, right? And it's in my interest too. So very rarely there is no conflict of interest, right? And here all of us want to learn, right? So, and now what do we know? The term inside the summation is
The whole thing is 1.
right, because np 1 plus, sorry, p plus 1 minus p whole to the power n minus 1. And again, I was not very careful about summations, but that's not my job, right? Whose job is it? You have to answer quickly. Yours, obviously. Whenever we do calculations, let me tell you from now on, I'm very, very lazy with that. And it's your responsibility to make sure that I don't forget any of the indices and anything, right? You have to point out if there is an error. Those are the things which you have done so many times. You're expert at it. I don't have to teach you, right? But the essential trick here was to create n choose k, n minus 1 choose k minus 1. Not a very, very difficult thing. But now let's turn to variance, right? Variance is expectation x square minus expectation x whole square, expectation x whole square taken care of, right? the problem is expectation x square. Again, don't shout out the answer. I want to know how many people can figure out expectation of x square. One. Thoda sa be proud of the fact that you could figure out expectation x square. You don't have to be shy. Two people. Okay, try it. It's a small trick again, but this trick is much more okay, very important. This you will realize many times. This is very, very important trick when you calculate these probabilities. Anyone from the backside who figured it out? Expectation x square. So then you can ask me questions, right? This is where I'm stuck. This is what is troubling me. Because that's like half the battle, right? In research, when you can figure out why you are stuck, that leads to answers, right? That's an important step. That's not the same as being stuck. So why are you stuck? What is troubling you while calculating this expectation x square? And let me tell you, it is going to be essentially the same trick as expectation of x, not very different. Okay, obviously linearity of expectation doesn't help us here. Let's write the formula for expectation of x square. Can you tell me what will it be? Looking at the expression above, it's just k square instead of k. And we can do the thing which we did last time. Have I got it correctly? One mistake here.
There will be an n-1 factorial above.
Sorry, there will be k-1, n-1 factorial. Good. Now I'm okay.
Yes.
This is the summation which we want to figure out. And now the problem is k-1. Right. So if we don't have k-1, we will have k-1. We can do plus minus 1, or again, very important thing is, if I want to calculate the expectation of x square, it is enough to calculate the expectation of, right? Because then we will get k times k-1, right? So why don't you calculate the expectation of x times x-1 and tell me this? N into n-1. Okay. Others, I want you to give it a try. Make sure that you can figure this one out. But this is the essence, right? This is where the how do I say it? Functions of random variables was helpful. We defined it. We said x, 2x, x plus 1. Everything is a random variable. We can talk about, if we can talk about expectation of x, we can talk about expectation of 2x. If we can talk about expectation of x square, we can also talk about expectation of x square minus x. And this is what is helping us here, realizing that expectation of x square and expectation of x times x-1 is essentially the same, not very different, right? And suddenly things become easy, right? Things will cancel out and you will see that the answer is, I need around 50% people to be able to figure this out. And if you are stuck, please ask me. This is why we are doing these exercises here. These are not difficult. You should be able to do them here. If you're stuck, please ask. And since the answer is given, you will take out n times n minus 1 times p square. Once you take that out outside, what will you get in the bracket? P plus to the power n minus 2, right? So how many people believe now that they can do this calculation? So people who are not raising their hands, why are you stuck? Please tell me anything which I can help you out with. Which one? Oh, that is not that. That is arrow. That's not equal. What I'm saying is that if I can figure out expectation of x times x minus 1, I can figure out the expectation of x square also. Right? Because what is expectation of x times x minus 1? Expectation of x square minus x. Right? And then what will you use? Right? I should have charged you 10 rupees every time you say linearity of expectation. But that's for the next course. That's for your juniors. Don't tell them that. Okay. So what did we get? What is the final answer? Variance of x is np into 1 minus p. You can finish this calculation on your own. I'm confident in you. If you are stuck, obviously there is hello. You can come to my office. We can clarify this. But this is not difficult. If you are stuck, you should definitely take help. Okay, there is nothing here which should not be clear after pondering about it for 5-10 minutes. Okay, so let me know if you are in trouble. Great. So we will go into the independence and all those things later, but you will see that we saw that expectation of x is expression of x1 plus expression of x2 plus xn. Is variance of x1 plus x2 plus xn equal to variance of x1 plus variance of x2 plus variance of xn? No, it is not. But sometimes you can simplify it, and that is for later when we know when we can simplify it, right? So we'll talk about independence and then we will do this. But for now, this is the way in which we can calculate. But you are right, there is a way, but that requires more background, which we will create in 1 or 2 weeks. Okay, good. Let's take one more random variable, which you have seen before. This was taught in terms of you keep tossing the coin till you get a head, right? Till you get a success. You might be a stubborn person. You go to the casino and say, I will keep playing till I win, right? And then if we count what is the random variable, it is the number of times you have performed this Bernoulli random variable experiment, right? So in some sense, again, the basic unit is Bernoulli random variable. You keep doing it and you stop when you get a 1. The probability that you have done the experiment k times is 1 minus p to the power k minus 1 times p. Is there any doubt about this form? Raise your hand if this is not clear. Why probability of x is equal to k is this quantity? Right? First k minus 1, I should get a failure. That's with probability 1 minus p. Last, I should be succeed. Now calculate the expectation and tell me what is the expectation. Now k will vary from 1 to infinity, k times the probability and I don't want to write infinity, because if I write less than equal to infinity, you will think of it as a number, and infinity is not a number. And this kind of I won't say it a geometric progression, but this kind of geometric progressions you must have seen before. I suppose in your JE exams or something? And so now you have to tell me what it is. What do you get? Okay. Expectation is 1 by P, right? So if you have figured out the value 1 by P, what is the trick here? Right. So in other words, you can, so if you want to be fancier about it, I don't know, in your math 101, 102, they covered this, but you can think of it as a difference of a geometric series, right? And that's why it will have an easier form. I don't want to get into analysis because essentially I'm not that strong there. So I will say that you can figure out this summation, right? Not a difficult summation. You can think of it simply as multiplying by 1 minus P and then seeing that two summations have a relation, right? Or you can think of it as differentiation of a Taylor series or a Maclaurin series and then simplify it. It's up to you, but you can figure this thing out, right? So if you just this k times x to the k, this kind of a series, if I call it S, I multiply it by x times S, correct? And then you know you will have a geometric progression. You can do +1 -1. You will create a geometric series and your summation series itself, right? So this is something which you must have seen. Again, questions, post on hello, one of your friend can help you. Otherwise, I can definitely help you. Not very difficult. What about variance? This is expectation of x square minus expectation of x whole square. Now expectation of x, you already know. This term will be 1 by P square. And again here, if you look at expectation of x square, it might be easier to calculate the expectation of x times x minus, which we did before. This is, I think, given as an assignment in the lecture notes. I will leave it at there. Please try it now, not before the midterm. If you are stuck, ask on hello. These simple calculations you should be able to do. Okay? If you are stuck somewhere, especially if you're worried about, oh, how did we get expectation of x square minus expectation of x square? Why is it equivalent to figure out expectation of x times x minus 1 instead of expectation of x square? These are the things which we want to figure out. Okay? Yes.
Sir, is it 3 by P minus 1 by P square?
Okay, good question. Are you talking about the variance or the expectation?
Variance.
Let me just see. I don't remember what is the answer. 1 minus P by P square. That will be the answer. Yeah, I was wondering if someone has a mic, but I realize now this is coming from the meeting. Still not accustomed to Zoom meeting. Okay. Yeah, so it's okay, right? Whoever is at the other end of the Zoom meeting, 1 minus P by P square. That's the answer you should get. Okay?
Okay, sir.
Okay. Okay. Now, in the last 15 minutes or so, we will look at another important thing, which is continuous random variable. These are not going to be that important for this course, but are going to be very, very important in general for life. Especially, you know, half of you will, as a probability statement, 50% with probability half, you're going to work in machine learning. And if you're going to work in machine learning, then you should know some of the continuous random variables, which you will kind of see many a times, right? And the difference again is going to be simple. Remember when we talked about continuous sample spaces, it was hard to assign probability to each point in the sample space, right? This is the same problem with continuous random variable, and that's why we define what we call probability density function, okay, instead of probability mass function, right? Probability mass function was for discrete random variables. We said probability of x is equal to k is this, probability of x equal to 1 is this. And now we won't be able to do it because we have uncountable number of points. If we assign them probabilities, positive probabilities, it's never going to stay in bound. So then we define what we call probability density function, which is not the probability of point x. Okay, so let me just write it clearly so that you remember with the thickest font possible. Okay, there is no way in some sense to define it, or if you want to define it, it will be z. What probability density function allows us is to figure out the probability of the interval. Okay, this is how you can say that your random variable will lie between 1 and 2. Your expected winning is going to be between, sorry, not your expected winning, but the probability that you're winning is between 1 rupee and 2, 1 rupee and 1000 rupee, -1 and 10 rupees. So your A and B can take different values, and you can calculate that probability by integrating. And again, since I don't like integration, most of the time you will be doing the integration. Okay, so the important concept is, one, it is not the probability. We call it probability density function. In some sense, it's the density of the probability. In that area, do you have high probability or not? Some sense of that. I don't want to say more than that. So it's not the probability, but it allows us to calculate the probability of an interval. Clear? This probability density function, you will see it many more times. You can read about it. Since this course is mostly focused on discrete random variable, I'm not going to detail here. Also, it is very obvious that the probability should sum to 1. It means the probability that my number will lie between -infinity and infinity should be 1, right? And this is what this condition is saying. So a probability density function is valid if this is the case, right? Obvious constraint. Yes, no, yes. And now if this is the expectation, this is how you are doing things, what should be the expectation? Integration x ranging from okay, for now, just remember this is how we define the expectation. Okay, very natural, how to go natural in the sense that, you know, pattern matching is very easy here, right? The way we defined expectation, then we took the integration, so we are also taking the expected value here. So once you now know this, we can talk about continuous random variables. We are going to talk about two continuous variables, random variables. First is exponential. This is only defined on positive real numbers. Okay, the probability is going to be positive only if you talk about numbers in a positive real range, so between 1 and 2. The probability that your number is between -1 and -2 is 0. That you should be able to figure out from this formula. My density of my probability is only there at positive points. Sounds good? And now this is just for example. And now once you know that this is the exponential random variable, this is fx. What is the expectation? Integration x is that okay? Right, it should be x fx dx. So again, not so correct way to remember it, but the way to remember it would be x occurs with probability density lambda e to the power minus, right? So this is the expected value. And since it is an integration, that means let me help you out. I don't know whether that was a help or not. Probably want lambda inside. Right, so I can assume that you can do the integration. If not, you can learn how to do the integration. Okay, so good thing when it is not my job, you can figure this out. It will come out to be 1 by lambda. Now, what is variance of x square? That's going to be expectation of x square minus expectation of x whole square. This you know is 1 by lambda square. This is going to be 0 to infinity x square right? Whatever is in the inside the expectation, that random variable comes here, the probability density here, and then dx. Right? This is the same thing which we did with discrete random variable. What was the expectation of x square? X square multiplied by probability, sorry, k square multiplied by probability x is equal to k. Same thing we are doing. Right? And even this, you can do it probably in twice as much time. This will come out to be, sorry, 1 by lambda square. Yeah, 2 by lambda square. Right? So that means variance is 2 by lambda square minus 1 by lambda square, 1 by square. Okay, this is for the exercise, but let's go to the more fun random variable. And this is the time when I should say wake up. Whatever is the case before that, I know a lot of calculations, you might be sleeping till now, but now wake up because this is very, very interesting. And that thing is hard to guess when you look at this complicated f of x is equal to 1 by square root 2 pi e to the power minus x. But this is normal random variable because it is very normal that you encounter it in a real life. And I will tell you why. Okay, so the importance of this, again, we will calculate the expectation, we will calculate the variance, all of that we will do, not that important, but I will tell you after this why is this important, and that's very, very important. Okay, so first let us look at this. Again, expected value is integral minus infinity to infinity. Okay, I should have said there is no restriction on x here. So expectation of x is minus infinity to infinity, x times this. Now you can do this calculation, or you can realize that Right. This function is symmetric, right? So the probability which is there before 0 is the same probability which you have after 0. So that means when you do this integration, you will get the answer. And then if you want to talk about variance, this is minus infinity to infinity. What should I write? Right, and then you will do some integration by parts, almost magic for me, and you will solve this integration. And the answer you will get is 1. Okay, you can't get 0 here, right? If the expectation was 0 and variance was 0, that means
The function is 0 itself.
exactly, thank you. The function is 0. Right? Expectation can only be 0. Sorry, variance can only be 0 when everywhere you are matching with the expectation. It is x minus ex whole square. Right? So normal random variable, this is, I have written it as star. This is actually not the standard random variable, not the general way in which you define a normal random variable. This is called the standard random variable, where your expectation is 0 and your variance is 1. And this tells you essentially all properties of even non-standard, because you do some kind of a scaling and translation and everything. Right? For example, if you want the mean to be mu instead of 0 in a random variable, you will just shift everything by, right? So you will just write your fx is 1 by root 2 pi e to the power minus x minus mu to the whole square by 2. And similarly, if you want the variance to be different, you can, when you calculate this variance, you can see that just by dividing by the standard deviation or square root of variance at certain points, you will be able to scale this normal random variable, right? And that's why general normal random variable looks like this. But that's not very important. All the properties of this non-standard random variable can be deciphered from the properties of normal random, where variance is 0 and variance is 1 and expectation is 0. And if you like integration, you can try calculating the expectation and variance of this fx also. And you should get mu and variance should be sigma square, right? Because sigma is the standard deviation, right? So yes, this was all about integration, but why do we like it? Why is it normal? Anyone already knows the answer? Okay, sorry, anyone still know the answer? My cryptic one statement was not of much help. Nobody knows the answer, right? So then please listen carefully. This is very, very important. This is called central limit theorem, but you will see many different versions of it in the course. The idea is that whenever you repeat a random variable multiple times, as n tends to infinity, the behavior of that random variable looks like a normal. Okay, and this is also called bell curve. This looks like this. Again, it should be symmetric, obviously. So that's the problem with my drawing. But you know, if you look at the picture of fx, it looks like this bell curve. And whenever you have a repetition of random variables, the final outcome, if you have lot of random experiments, I will give you examples, the final behavior should look like this. Let's start with Bernoulli random. If that's the basic random variable, if I repeat it multiple times, I get the random variable. Which one? We just saw it today. Everyone should be able to say it. x1 plus x2 plus xn, where x1 is Bernoulli. You get binomial. Was that a surprise? No, right? It's binomial distribution. So this is again binomial distribution is a distribution of the kind x is equal to x1 plus xn. And actually, I should not say binomial distribution. I should take the related distribution, which is the average of this. And then call it, let's say, x prime. As n tends to infinity, x prime will resemble like a bell. It will look like a normal, with the expectation of that would be expectation of x. And the interesting part is, it does not matter what is your x1. Here I took as an example Bernoulli random variable. You can take any distribution which you want as x, whichever one you like. If you repeat it multiple times and takes its average, it will look like a normal. That is why you see normal random variable so often. Think of it this way. You pick a person in an entire sample of a village. Do they have cancer or not? This distribution could be whatever, I don't know. It could be Bernoulli. It could be Bernoulli with any parameter p. I don't care. But if I take the probability distribution of how many people are suffering with cancer in a village, right? That's like talking about x prime, and that will be a normal. So if you take lot of villages, if you plot out, what do you say? If you plot out the number of people having cancer, you will see this kind of a graph. So whenever you are plotting any average random variable, you will see a normal behavior. You can start with any distribution. If you repeat it multiple times and divide by n, the behavior will look like this. Do I make myself clear? You go to a casino, you can win with 0 with some probability, 1 with some probability, 2 with some probability. If you go to casino infinite times, or if you go to casino many times, your earning will be distributed like this, because that's an average of a random. That is the power of the central theorem. And that is why you see bell curve so often. Whenever you want to, I want to look at marks of a class, right? Marks of one student would be distributed, I don't know. It might be very, very different, might depend on things like that. But if I look at class marks of sections like first year of 1991, 92, 93, 2000, and assume that course syllabus was same and everything, and then if I then plot them, it will look like a normal random variable. Many people extrapolate to saying that everything behaves like a normal random variable. That's not true, right? So many properties in life behave like normal random variables, and what central limit theorem tells us is, if they are distributed as an average, if you take a particular experiment, repeat it many times, as n tends to infinity, you will look at this distribution. We will not look at central limit theorem, but we will see many versions of it, Chernoff bound and others, where we will see how to mathematically formulate this, that we are very close to expectation with very, very high probability, right? So as n tends to infinity, this bell shape becomes more and more prominent, right? In another thing it is saying is, since this peak will happen at the expectation, it gives you the meaning of expectation. If you repeat the experiment many times, the average of that will be your expectation with high probability, right? Expectation of this thing is same as expectation of x. This follows by linearity of expectation, but it is also a statement. Okay, sorry for taking 3 extra minutes. I will see you on Wednesday, and I think there will be a quiz. How can we keep the quiz? Should I keep it in the night, like let's say 9 to 9:15 or something? What might be a good idea?